All right, guys, welcome back. So, continuing on for the core effects on the blue stuff. Let's talk about how we've done the this volume core. It's literally just particles that were rasterized into volumes. So let's get to it in Houdini now. So all it is just this crazy volume volume sphere with some temperature in it. It was literally just some particles that are swimming around the sphere. Yeah. So let's get to it. So if you just put down a sphere and plug that in into a pop net, and all we do is just scatter on the surface, and as you can see, we play the sim, it scatters a bunch of points onto the sphere. But obviously this is a bit boring, so we want these particles to spin around a certain axis. So I used a pop axis force for this, and it's just gonna be, it will just be spinning around whatever axis direction we put in here. So this is cool. It's working somehow. All we gotta do is click on add some more orbit speed into the whole sim. So we can see how these particles are moving around the sphere. But it's also um, coming off of our sphere, and we obviously don't want this to happen. So all I did to stick these particles onto our input mesh here is by using a pop wrangle, and there's a function called min pause. So this min pause just gets the closest position on the surface of a geometry, and that geometry will be the sphere that we plug into the solver. So all we gotta do is under inputs, I'm just gonna put input 2 to tell it to read from the first context geometry, which means that this input of this node, the first context geometry, and put that into input 2. So I'm going to do min pause, and we read that geometry, and because the min pause function just takes the geometry, input geometry, and point as the arguments, the point means position. So I'm just gonna put in 1 and position. Cool. And it returns a new position for us. So if we just put it this way and we play, nothing happens because we haven't done anything to our position. So we just put at p equals new pause, and we'll see that these particles spin about the input geometry that we made up here. Cool. But we also want these particles to come off a bit from the sphere. We don't want it to be sticking all the time to our sphere. So all we gotta do is just mix between our current position and this surface position, new position. So the function is lerp, which just performs a linear interpolation between the two values, and these two values we provide are our current position and the new position. And I'm just gonna tell it to blend 50% to the new position. So you can see how these particles are now coming off a bit from our input geometry. So that's pretty cool. And another thing I want to add is some general noise. Let's increase that a bunch of times. Oh, that's way too crazy. So what about this? So you can clearly see that these particles are trying to stick to our sphere position. It's not too bad. Maybe just one then. Cool. All right. But now looking at this closely, I kind of want to have two directions. So one is spinning around a certain direction, around, in this case, it's spinning around the y-axis. I want 50% of the particles to, say, spin in the x-axis instead. So if you check this guy, so you see not all of them spins. I've got literally two velocities spinning in two different directions. So all I did for that is we have to overwrite this axis direction, and if you just click on the use vex expressions and click on this drop down button, and you can see the pass through. This is a preset, so pass through just means passing the same value to the parameter. So type equals type, that would be this, center this, axis would be the axis direction, radius would be this, and the height would be this. So for our purposes, we just need to take in the axis. So all I'm going to do is do axis equals axis. All right, so what we want to do is say we want to have two directions. So there one would be, let's try around x-axis. Then there two would be around the y-axis. So the way I blend between these two directions for the state of the particles is the exact same thing I did here. So I'm just gonna copy this, put this down, and say, hey, I only kind of need, what about just 50% of the particles moving on the x direction and the other 50% orbiting around the y direction. So we shouldn't be doing, I'm just gonna copy this here, paste that there, and axis would be here. So we need to say rand at id greater than or less than 0.5, it doesn't matter in this case, 50%. So what this does is just say, hey, let's just take 50% of the particles that we have currently on the frame and tell it to move either on dir1 or on dir2, because this condition is just a Boolean operation, so it's just a 0 and 1. It's not, there's no interpolation from 0 to 1. It's at 0 0.2, 0 0.3. This just gives you literally 0 and 1. So you will just have two directions essentially, which is the x direction and the y direction. So if you check this now, you can see our velocity vectors spinning along one direction and the other direction. Cool. Nice. So as you can see with the velocity vectors, we're not really getting accurate calculation, because on our pop wrangle, we're forcing a new position every frame in this expression. So what I did to fix that is just recalculate the velocities in a SOP solver. So we just put down a SOP solver and plug it into the merge, and just say put down a trail node, compute velocity, backwards difference, doesn't matter, I'm not sure, and just plug that in to the stream. So now we're getting slightly more accurate velocity readings. Cool. So another thing that I wanted to to show is how I get these clumping of the particles. I've really just done it in the simplest way that I thought. So by putting down, just let me add some more particles into the sim. So by putting down in the SOP solver that we just created, by putting down an attribute blur, we can say, why don't we blur our velocities with our neighboring points? So just tick off pin border points and change the influence type to proximity. Proximity doesn't care about the connectivity of the particles, but proximity is just based on spatial radius, which is this thing. All right, so if you have a look at this, we're getting a bit, some clumping here and there. If you change this to a higher number, and we'll get some nice, this blurring iterations. We get quite a lot of clumping. Well, we have to reduce the proximity radius lookup. Yeah, we get some clumping here now. Cool. And another thing I did was I'm not only blurring velocity, I'm also blurring the position. So you just put this down to a decent number. Now we get a bit of some more clumping. Awesome. Now, as you can see, we're kind of picking up this quite a very uniform, slightly uniform noise pattern into our sim. So the way I kind of fix that is to generate an emission attribute. So under the pop network, on our pop source, under source tabs, we can say, why don't we, instead of scattering points randomly on the sphere, why don't we specify which areas of the sphere that we want to scatter from? So the SOP solver, the pop source node has this emission attribute that we can set up in SOPs, and all I did was, it's literally this node, copy that, put it here, and inside this node it's just a noise that I plug into an emission attribute. So all we gotta do is create a point VOP, and in this point VOP we just stick a anti-alias flow noise, plug that into the position, and let's visualize this noise. Find export emission, and let's have a look at this noise. We've got the color sub, I think, that visualizes that noise. And now we can see a pattern on our sphere, and I kind of want this noise to move around in time. So all I did was to just create a vector to 4, vector to vector 4 position. So our fourth dimension would be time, and if we plug that in, now we can see our noise pattern moving. Cool. So that's it. That's onto emission, and under the pop net, quit that. Just plug that emission there into the emission attribute, and we should have points scattered onto the areas where we want the scattering to be in. So as you see, we've got red here, so we should expect more points to be scattered on that area. And on the purple side, we should expect no points to be scattered on these areas. Cool. So this would hopefully break up the scattering of our particles. And awesome. So that's really pretty much what I've done in my little pop net here. Zoo, 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 zoo. So if you just have a look, what I've done inside, all we did is just grabbing the surface position, the pop, I added pop force into here, and then doing the random axis direction, and that's pretty much it. So if you go down the subsolver, I can delete this. That's nothing. It's just blurring out the V, blurring out the P, the position, and recomputing the velocities. Nothing too special. And that's how I got this thing. So after doing this, I just let the sim run for a few frames, cache that out, and then on this attribute VOP, I'm just applying some noise onto the sphere. So we kind of get ourselves, if you just zoom out, we can see almost a perfect sphere shape. So this helps break that shape up. Not too much, but just enough to remove that basic spherical shape. All I'm doing here is just normalizing the age so that I could use it for some coloring. It's nothing special really. I'm just saying, why don't we have this color when we're born, and as we die, we become a bit brighter. It's nothing special, and I'm just transforming the particles down when it collapses into itself and recomputing the velocity, so I get this cool looking. If we have a look at the core pass, you can see how the velocities collapse into itself. So that's cool. Whoops, oops, oops. All right, so next up, I've got these orange colored nodes are my little HDAs. You just wrap up simple basic operations that I find repetitive. So this quick rasterizer is just rasterizing volumes, literally just a volume rasterize attributes. And in here, I'm just putting in density. And if you have a look at this thing, I need to pause for a bit. Where's my density? Oh, because
you gotta move it back.
No, there's no density. So my HDA actually just initializes a density if it doesn't exist. So see, if I put here, quick rasterizer. If you check this inside, this thing, if there's no density present in the input point particle, then it's gonna create a density attribute with a default value of 1. So that's why. So this one doesn't stop working because I have to do. I can just say attribute create. Huh? No, I'll just cut it later. This is density.
Checking on you, right?
Yeah. Put value of 1 here, and you can see that it's there. Cool. Just gonna put it like this. And yeah. So I'll delete that.
Yeah, okay.
Alright, so these orange nodes here are just my little HDAs that are just literally just wrapper for quite repetitive tasks, and they're just simple tasks. So this quick rasterizer is just a simple volume rasterize attributes node. So I don't have a density attribute here. So what I'm gonna do is just put in a wrangle and this wrangle I'm just gonna initialize our density so we can rasterize that attribute here. So by default, it's gonna look like this. It's gonna bring down the particle scale, the voxel size, just to get a better look. So it's literally just this, and we can blur out the smoke with our velocity, so we get nice streaks. Otherwise, we'll have these dots, voxel dots here that look a bit odd. So just turn that on, and then we get nice streaks. So that's what this quick rasterizer is doing with extra stuff like dissipating, multiplying down, scaling down the density over the particle's normalized age, and that's it really. It's nothing fancy. So if you want to replicate it in a wrangle, you just have to say f at density is equals to 1, and what we can do is f at density times equals f at normalized age, but we feed that normalized age into a ramp so we can have more accurate control. Age density, and there we go. So let me double check if we have that attribute normalized age. Yep. So if you see, now we're removing some of the particles with density over we're scaling down our density over the normalized age of our particles. Nothing too fancy. That's it really. And then this volume self-advect is just re-advecting, is doing another pass of volume blur, volume motion blur. So all this node is doing is simple as doing a VDB advect. So if you put that down, and all this needs is the VDBs that we want to advect and the velocity VDB that we use to advect the source VDBs. So what we need from our volume rasterized attributes is a velocity that we can get from the rasterized attributes. Okay, so cool. So I'm just gonna plug that in here, and then this in there. So what I'm gonna do is say our velocity, we advect the density with our velocity, and that's pretty much it. I'm just gonna say use BFE CC for the advection scheme and clamp to extrema for the limiter scheme. That's the defaults that I've seen other people do, so I'm just gonna follow that. I'm not sure what they do, but I'm just gonna follow what I see. All right, so as you can see, we're getting some extra pass of streaking. I'm gonna increase the resolution a bit. After, you get more streaking, and we get nice deformations as well on our volumes. Cool. So if you dive into this VDB, you can see what I'm doing here. I'm doing some extra passes, extra post-processing, pre-processing of the VDBs as well. So if you put down VDB smooth, and we can smooth out the velocity before we advect our sources. Oops, sorry, not that node. VDB smooth, VDB smooth. There you go. Put that down, and then just say smooth out the velocity, and that should smooth out our velocities, and we get a totally different look. So without and with.
Why not pick the smooth SDF?
Because smooth SDF is meant for It's meant for SDF,
Mm.
sign distance field. You know, like this one. This one is smoke. Volume velocities are smoke as well. So if put this here, and then VDB fog to SDF. See, this is SDF. And this one, VDB smooth SDF, only works with VDBs. Alright, so that's what that node does. And I've got 4 volume sharpens here. They're just sharpening the density field and the temperature field. All this is doing is literally, so it's just a convolution kernel that sharpens, that takes the neighboring voxels and grabs value from it and do some cool processing. So all the way I took that technique from is like putting down the pyrobake volume. And the pyrobake volume has this cool little thing under quick setups, and if you just put in sharpen volume, and it gives this subnetwork down for us. And if you dive into that subnetwork, we can see what side effects is done here. And all I did was just copy this node and run it for each number to say how many times do we want to sharpen the volumes. Just be very careful with this technique. It can make your volumes look funky. So all I'm doing here is say, why don't we run a a sharpening kernel 5 times. So I'm gonna plug that here and say, not merge iteration, but feedback each iteration. So you can see remove that. And interesting. Oh, nothing's happening. Oh, let us see why. Okay, fetch feedback. This is not fetch input. We have to put fetch feedback. Okay, so I'm gonna put back again. I'm gonna re-say that. So all I'm doing with these nodes from side effects is just run that through a for each number block and set this block to run to fetch feedback instead of input. And the gather method would be feedback each iteration, and we just simply plug all these into the for each block. And now you can see the effect that gave. Obviously this is way too much, so I'm just gonna say, why not just 3 iterations, or maybe 5. Just be very careful with this technique. It can create artifacts on your volumes. But yeah, that's really what I did for this HDA. I ran the temperature through the volume sharpening as well. And this is what we get. Super cool. So the temperature, if I forgot to mention, I just, in this quick rasterizer, I'm just copying the density into a temperature field. So as you can see here, I'm rasterizing just the density in V, but I'm also gonna be I also need a temperature field. So all I'm gonna do is isolate the density. So all we have is density here now on this stream, and then rename that density into temperature. And so it's the same exact field, just a different name, temperature, and just merge that back in to this stream. So now we have density V and temperature. Run that in here. And that's what we get. If we check this with the pyrobit volume, now we have some temperature field. Without this, we won't have any temperature field because we don't have temperature. So put that in there. And now we have fire. Cool. So that's all I did for this part of the core. Really simple, really easy. And yeah, that's pretty much it. I'll see you on the next video.